Okay, so our quick look at the calendar tells us that today we are working with radicals. I'll just give you a reminder that radicals and powers are one of the toughest topics for many 096 students. So keep pushing, be patient with yourselves. There's a lot of ways to get problems wrong and often only a couple of ways to get them right in these sections. So again, on page 14, we'll start at the top. Virginia, can you read us the summary? Okay, so let's take a look at number 1. We'll go to, who's ready? Casey? Okay, let's write down these two numbers. What two numbers, when you square them, give you 25? 5 is one of them. -5 is the other. Everyone agree? Two numbers, when you square them, you get 25. So in general, all positive numbers have 2 square roots. We just found the 2 square roots of 25. They are 5 and -5. And so all the time, one of them is negative and the other is positive. Now, there's an important distinction between me asking you to find all the numbers that when you square them, you get 25, and me asking you to find the value of this symbol. So we've seen this symbol many times in other classes. That's called the square root of 25, and the square root of 25, according to that symbol, is the positive square root of 25. So this is equal to 5 only. It is not 5 and -5. It is not -5. It is just plain old 5. So there's a difference between asking for the square roots of a number and that symbol. That symbol indicates we are looking for the principal or positive square root of 25. Okay? All right, moving on to number 2, there's some vocabulary according to this symbol I'll highlight here in green. And here's some vocabulary. It says x is called the radicand. That's the thing underneath the square root symbol or the radical symbol. The n is called the index. That's that little tiny number in the front. We'll talk about that guy. And then finally, that symbol itself is called the radical sign or radical symbol. So here are some examples of radicals that are not square roots. How would we read this first one in number 3? How would we say this symbol out loud? It's the cube root of 64, right? It's a number that when you multiply it by itself and then by itself again for a total of 3 copies, we get 64. What is that magic number? 4. So the cube root of 64 is 4. And then the next symbol over here, that's the 4th root of 16. It's a number that when you multiply it by itself 4 copies, gives you 16. What is that number? 2. Okay, moving down to number 4. We've already seen that the cube root of 64 is 4, right? That's what we wrote right up above. But instead of writing 64, I could write 4 cubed. Isn't that the same as 64? And so then if you see the cube root of 4 cubed, without actually building it up to 64 just to bring it back down, we could just kind of say, well, wait a minute, the cube root and the cube are opposites of each other, right? And so they just cancel, and so we just get 4. And so then in general, if I see something like the cube root of x cubed, what is that equal to? It's just plain old x. So this is equal to x. And then the same idea in number 5, the 4th root of x to the 4th. 4th root and 4th power are opposites. They cancel each other. So what is that equal to? Just plain x, right? So if that index, that little tiny number in the front, exactly matches the power, then they're undoing each other, and you just get the thing that was underneath there to start with, just plain x. Okay, number 6 says we're going to show all of our steps in simplifying this thing. It's the cube root of x to the 21st. There are a lot of things that we could think to do with that 21 and that 3. We could add them, subtract them, multiply them, divide them. Turns out only one thing is correct, and I don't want us to just like memorize it, at least not at this stage. So here's what we're going to do. I'm going to start with the cube root of x to the 21. And I'm going to follow a process that I'm not going to expect you to follow. Like once we get to the shortcut at the end, you're welcome to use it. But I don't want to just throw the shortcut up here and say, hey, memorize this because Ian says it's true. So here's what we're going to do. Would you guys agree that if I could somehow rewrite the problem in this form, I don't know what goes in the blank in the parentheses, but if I could somehow rewrite it in that form, then the cube root and the third power would cancel, and I would just get whatever's in the parentheses? We buy that? Isn't that what this thing up here said? Is that if you have a cube root and a cube, then they just cancel and you get whatever was in there in the first place, just x? So can we figure out what goes in the parentheses here? Well, let's see. I know it was x before. It was x to the 21. So I need to put some power up here so that when I cube it, I really get the same x to the 21 I had before. Jasper? So Jasper thinks maybe 21 divided by 3, which is 7. Do we buy that? Like if I put a 7 right up there, so if I make that a 7 and then just recopying the cubed, we know what do we do with those powers up there? We multiply them. That's what we do with powers. When you have a power to a power, we multiply them. That was one of our rules. So how many x's do we have right now? 21, the same as what we started with. So it's completely equal to what we had before. But then we've got this nice pattern which says, wait a minute, cube root and cube are opposite. And so in a very real way, we can just cross them off. And what's our final answer here? Is x to the 7. That's it. And so then we do have a shortcut, and Jasper essentially led us there. Whoa. Yeah, so if they're not divisible, all right, so let's talk about the shortcut, and then we'll talk about what if. So what did Jasper say we should do with these numbers here? We should divide them. That 21 divided by that 3 becomes the new power of 7. And that's it. That's the shortcut. So what if it's not divisible? Well, we'll see down here what we can do if it's not divisible, and next class we'll also see lots of things when it's, we'll see what to do when it's not divisible. But for now, most of them, we'll just pick them to be divisible. Okay, so number 7 says that if it happens that this value of k is a multiple of the value of n, meaning it's divisible, then we can just divide them. So this is exactly what Jasper suggested we do, right? Take k, divide it by n, stick it up there on the power, and that's our answer. So then in number 8, maybe don't say this out loud, but just write your answer. If you understand this whole rule that we just talked about, then this is like a 2-second problem. What did we decide we were doing with those powers? Dividing them. So this is x to the 20 divided by 4. In other words, x to the 5th. That's it. Okay, so this problem is really easy because right in front of us is the rule that says divide them. But if this problem is mixed up in the middle of many other exponent problems, it's not as easy. So we just have to start recognizing when we have something that looks exactly like this, where there's a radical and you've got some small number in the front there and a power on the variable, that's when we divide them. We don't add those exponents, we don't multiply them, we don't subtract them, we divide them. Okay, number 9. It says find the value of each of the following radical expressions. So the first one is the square root of 9 times 4. So let's do that multiplication and then we'll take the square root. 9 times 4 is 36. Square root of 36 is 6. And again, notice it's not plus 6 and minus 6, it's just 6. That radical symbol means just the positive one. And now let's do the square root separately and then multiply at the end. Square root of 9 is 3 times square root of 4 is 2, which is 6. And it turns out these two guys will always be exactly the same. And this is illustrating a nice property of radicals, is that if you have a product inside of a radical, you can split it up into 2 radicals and multiply at the end. And that's what's written down here, this product rule for radicals. It says if you have a product inside, you can split it up into 2 radicals, multiply them at the end. It turns out that division works equally nicely. If you have a fraction inside of your radical, you can make it 2 radicals and divide it at the end. So let's see how we're supposed to use these 2 new properties in number 11. So we're trying to simplify the cube root of 16x to the 10 times the cube root of 2x to the 19. And you can see it didn't take long today for us to get to some really messy looking problems. Okay, first observation, they're both cube roots, which means I'm allowed to use this property we just saw about the multiplication. I have two radicals multiplied together. It's exactly the same as one radical with everything multiplied underneath. So that's our first step. 16x to the 10 times 2x to the 19. Everybody see that's the property that we just observed? You have two radicals multiplied together. You could smush them together and make one radical. And now we're going to combine all our stuff inside the radical. So we're going to mush together the 16 and the 2. So that's 32. What do I do with the x powers? I'm going to add those guys. So that's a 29. Okay, so far so good. So here's the new part to this problem. You can't just stop here, because even though the cube root of 32 is not a nice number, right? There's no nice number that when you multiply it by itself 3 times, you get exactly 32. Let's see, like 2 times 2 times 2 is how much? 2 times 2 times 2 is 8. 3 times 3 times 3 is 27. And that's really close to 32, but then 4 times 4 times 4 is 64, which is way too big. So the cube root of 32 is something between 3 and 4, but it's not a very nice number. But here's the twist. We're going to take this radical, and we're going to re-break it up. So I'm just going to kind of make 2 empty radicals. And my goal is to put stuff that has a nice cube root in the first radical and put everything that's left over into the second radical. So one more time, 2 times 2 times 2, 8. And doesn't 8 go into 32 perfectly? So that means that I could take that 32 and I can factor it into an 8. And what's the other factor? It's 4, right? Everyone agrees 8 times 4 is still the 32 that we had. And we'll deal with the x's. But the nice thing is that the cube root of 8 now in that first symbol is a perfectly wonderful number. What is the cube root of 8? It's 2. And so we factored the 32 into something nice, something that has a cube root, and then whatever's left over. Now, just as well, we could have factored the 32 into, what, maybe like 2 times 16? But the cube root of 16 is not a nice number, and neither is the cube root of 2. So you can't just willy-nilly factor any way you want. You're factoring with a purpose. You're factoring so that you find a perfect cube root or a perfect square root or whatever you have. Okay, so we took care of the 32. X to the 29. We're going to split these x's up as well. Okay, Jasper's idea was that we take the power, the 29, and do what with it to that 3? Is divide it by the 3. Is 29 evenly divisible by the 3? No. So it doesn't go in nicely. So here's what we're going to do. We're going to start peeling off some of those 29 x's that we have to play with until we have a nice number, a number that's divisible by 3. So suppose that you take those 29 x's. You don't need to write this, but suppose that you split it off like that. I still have 29 x's. Yeah? If this was underneath the cube root, does 28 divide nicely by 3? No. Okay, so that wasn't so great. Let's peel off 2 of the x's. I still have 29. Is that 27 nicely divisible by the 3? Yes. So this is the right way to split apart the x's. You had 29 of them. You peel them off until you get something good. And so that good part we're going to put into the first radical. So I'm going to put 27 of my 29 x's there, which leaves how many left over in the other one? 2. Yeah, and finishing this is going to be pretty straightforward. But the tricky part is that step right there, because we treated the 32 and the 29 completely differently. We looked for a perfect cube that went into 32, right? We're looking for a perfect cube that went into 32. We said, oh, 8 is a nice number. 8 is a perfect cube. And then whatever's left over, it was 4 in this case. But the 29, we weren't looking for a perfect cube that went into 29. we were looking for a perfect, we were looking for a multiple of 3 that was less than 29, because Jasper's rule was that we're supposed to divide these powers. And so we're just looking for a number less than 29 that was divisible by 3 in this case. So this is really tricky. With some practice, you guys will get good at this. And let's finish here. The cube root of 8 is 2. Cube root x to the 27, what do we do with the powers? We divide, and we get x to the 9, right? Divide. And then I'm just going to copy the rest of it. And that's the end of that problem. Because again, the cube root of 4 is not anything nice, so we can't simplify it. And the cube root of x squared is also not anything nice. So we split into 2 radicals, nice stuff in the front, whatever's left over in the back. We simplify the nice stuff, and you just copy what's in the back. Okay, number 12 asks us to consider square root of 9 plus square root of 4 compared to square root of 9 plus 4. So let's do the addition way first. So what's the square root of 9? 3 plus 2 is 5, so that's definitely equal to 5. No big deal. This is the same as the square root of 13, which isn't a very nice number. In particular, is it equal to 5? No. So why am I showing you this example? Adding doesn't work. You can't do something that appears very natural. It seems very natural that the square root of 9 plus 4 should be the same as the square root of 9 plus the square root of 4. Just looks like it should work, but it doesn't. So you can't use it. But this is really different from the property. Just go look real quick on the on the bottom of the previous page. You see something that says square root of a times b is the same as the square root of a times the square root of b. That's a property that works. And so it seems perfectly reasonable that the square root of a plus b should equal the square root of a plus the square root of b. But it doesn't. And so this is another one of those times where there's so many things that look right that just aren't. And so down here is an important note. Let's go to Dan for 13.
Radicals of square root of x plus y and minus y.
Okay, so really I want us to be very clear. Just write some angry lines, you know, like picture like some face of some person you don't like and just start scratching it off. It just doesn't work, okay? You cannot do anything with the square root of x plus y or the square root of x minus y. Addition and subtraction inside of a radical, can't do anything. Okay? Multiplication and division, they work nicely, but not addition and subtraction. Okay, 14. Let's just jump down and do some examples, actually. Let's go to part A here. It says 5 radical 7 plus 3 radical 7. I'm going to translate that for just a second. I'm going to call this 5x plus 3x. You guys agree that just x is the square root of 7 is a perfectly good substitution? So how much is 5x plus 3x? 8x. So we have no problem saying this is 8x. So by the same reasoning, we should have no problem getting the answer here. 8 square root of 7. That's it. It's just 8 square root of 7. But again, this is another moment where you can make a mistake because you can say, oh, square root of 7 times the square root of 7, maybe that's just 7. Or maybe we're supposed to multiply the 7s and get 49. Or maybe we add the 7s and get 14. But you don't do any of that. Because 5x plus 3x, you don't do anything with the x. It just sits there. You're counting how many x's you have, so it stays x. It doesn't change. Jasper. Okay, let's take a look at B, which looks a little bit tougher. Square root of 12 minus 2 square root of 75 plus 7 square root of 27. So these guys right here, we cannot combine. Not at the moment, because this x is not the same as this guy, which is not the same as that guy. So the only way we can add and subtract these radicals is if they're exactly alike, meaning the same thing under the radical and the same index. But what we're going to do first is we're going to simplify each of these radicals separately, and then maybe we can combine some stuff at the end. So this is equal to 12 has a lot of factors, and we know that multiplication under a radical works really nicely. So you could write 12 as 6 times 2. Don't copy this until we decide which one we're going to choose. Or you could write 12 as 4 times 3, right? Two perfectly good ways to write 12. And we know that this square root works really nicely, so this is the same as root 6 times root 2. Again, you're not copying until we figure out which one we want. So these are both valid, but which is the one that we can simplify? Yeah, the square root of 4 is a nice number. What is the square root of 4? It's 2. The square root of 6 and the square root of 2, we can't go any farther with them, but the square root of 4 we can pull out and make it just plain old 2. So that's the one that we're going to use. Again, it's not just a random factoring, it's a factoring so that something nice happens. So we've decided we're going to rewrite the square root of 12 as the square root of 4 times 3, which becomes square root of 4 times square root of 3, which becomes 2 times square root of 3. That's as far as we can go with the root 12. Okay, let's try the same thing with the 75. There are a lot of ways to factor 75. I don't want you to just sit here thinking through the factors of 75. What you want to do is have a purpose. The purpose is to find a nice factor of 75. Nice meaning a perfect square like 4. So some of you might just immediately have it in your head, but if you don't, we've got up here in yellow, the bottom row is the perfect squares. And so honestly, we just go one at a time through these numbers in the bottom row and ask, do any of them go into 75? Does 4 go into 75? No. Does 9 go into 75? No. Does 16 go into 75? You may not know, but I mean, 16 is even and 75 is odd, so no. Does 25 go into 75? Yes. And so that means that we're going to take that root 75 and write it as a root 25 times whatever you need to, and 3 in this case, okay? So don't just factor arbitrarily. Don't sit there spinning your wheels finding any factor you can. It's a very selective kind of factoring. And then we can split it up because radicals over products work really nicely. And then that square root of 25 comes outside as 5. So it's just 5 radical 3. Now there's one thing that I ignored in this red stuff. What did I ignore? Is that there was a minus 2 in the front. Okay, so let's just plop it back in the front. It's minus 2, right? And then it's a minus 2 there. And then it's a minus 2 there. But now I need to put in a symbol because that looks like minus 25 and that's not right. So what symbol is the one that's in here? Yeah, it's times because that 2 really had an invisible times next to it the whole time. So we'll put in a dot, negative 2 times, negative 2 times, negative 2 times. That's good. And then we'll do the same thing with that square root of 27. So the square root of 27, you just play the game looking at this bottom row of yellows, and you say, do any of these numbers go into 27? Which one? 9 goes in. So we write it as 9 times whatever we need. 9 times what is 27? 3. And so that becomes square root of 9 times square root of 3.
Is it deliberate that all the triangles are further, all the
You caught me.
because if the triangle is have a problem.
Right, it's not going to match up nicely for every problem. Yeah. Okay, square root of 9 becomes 3. Square root of 3 is sitting there. What did I not copy down? 7. So there's a plus 7, plus 7, plus 7 times. Times. Okay, and now we're going to clean up. I think we got just 2 steps left here. So the 2 radical 3 we can't do anything with. But we can multiply the 2 and the 5. So this becomes a minus 10 radical 3. Notice that that 2, this 2 right here, doesn't hit the radical 3. I mean, it doesn't become 6 or anything like that. It's just, this is just a plain multiplication of 3 things, and we chose to group together the first 2. But the 2 doesn't distribute, certainly doesn't go inside a radical. And then the last one out here is a plus 7 times 3, 21, 3. And now finally, because as Sam points out by a coincidence here, they all are just radical 3s, we can smush them together. So you have 2 of them, and then you subtract 10 of them, and then you add 21 of them. So how many do we have altogether? I get 9. 9 radical 3. Right. So if it didn't happen, like if these were different numbers here, like this was a 5 and this was a 2, then this would be our final answer. We wouldn't be able to go any farther. Nate? Did I not subtract right? 21 minus 10 is 11 plus 2. I did 11 minus 2. It's a Friday. I wanted to see if you guys were paying attention. 6, 11. There we go. Thank you. Okay. We're good now? What is wrong? Wait a minute. You're still paying attention. Oh, wait. 21 minus 10 is 11 plus 2 is 13. 11, no, 13. Radical 3. All right. Good. Okay. So we got that. All right, let's, there's one last idea for today, and then we'll jump into the group activities. So let's find the following 2 things. So the square root of 5 squared and the square root of negative 5 squared. So first of all, we're not going to do any shortcuts here. We're just going to do the calculation. So the 5 squared is really 25. And what's the square root of 25? Is 5, right? Not plus or minus 5, just 5. That's what that symbol means. And then over here, this is the square root of, okay, how much is negative 5 squared? Is it positive 25 or negative 25? Positive, because the negative is getting squared. So that's positive 25. And then what is, that's also 5. Okay, but there's a problem here. We said earlier that the cube root of x cubed is the same as x. And so by the same token, the square root of x squared, like I'll just put, there's an invisible 2 there when you have a square root. What is that equal to? Seems like it's just x, right? So then looking at the original problem, square root and squared should cancel, and I should just get 5, right? And did we get 5? Yeah, super. But in the other one, the square root and the squared should just cancel, and I should get negative 5. Did I get negative 5? No. So when we wrote earlier that the 4th root of x to the 4th was x, we lied. It's actually not. It seems reasonable, and if the x is positive, then it's true, but it's not true all the time. So let's fix it. It's something like that. We gotta update it to make it true. So here's the idea. If we start with 5, we end with 5. If we start with negative 5, we still end with positive 5. So what's the name of the mathematical symbol that takes a number and makes it positive no matter what? It's the absolute value. We've seen absolute value before. It takes a number and makes it positive. So that's the answer to this one here, absolute value. Which means that, for example, in the next line, the square root of a squared, it feels like it should just be a, but really, it's the absolute value of a, right? Because whatever a is, if it's positive, it's just going to come out and stay positive. But if a happened to be a negative number, like negative 5, it's going to turn into a positive 5. Okay, so let's look at 16 and see if we can kind of really identify when do we have to deal with this messy absolute value idea. Okay, cube root of 5 cubed. Okay, let's actually do 5 cubed. So if you don't know it, our perfect cubes are over here in green. So how much is 5 cubed? 125. So this is the cube root of 125. And the cube root of 125 is 5. That seems perfectly good. Let's see what happens on the negative side of things. If you do negative 5 times negative 5 times negative 5, is it this or is it negative? It's negative because we have 3 negatives. And then what magic number, when you multiply it 3 times, will give you negative 125? Is negative 5. So let's see. In the first example, the 5 came right out and got copied as a 5. So far, so good. The negative 5 came out and got copied as a negative 5. So it didn't become positive in this case, right? So there's something different between the square root example we did above and the cube root example we just did below. And I'll just kind of write the punchline here. The 4th root of 5 to the 4th turns out to just be 5, and the 4th root of negative 5 to the 4th turns out to also be 5. So when do we have to bring in this absolute value business, Julie? Yeah, it's only when we have even exponent and even index. Okay, so 17 is our big conclusions. I don't know if this mnemonic is lame. I was kind of tired when I made it up, so here it is. If n is odd, then we don't have to do anything, right? You don't need to bring in the absolute value. You just get plain old A. But if n is even, Julie just told us that we do need to bring in the absolute value. So if that n is even, the answer isn't just plain A, it's actually absolute value of A. Fiona. So really, if I'm writing my workout for this green one here, I would say, okay, it should be negative 5, but really, because it's even, it's the absolute value of that, which is just plain 5. You can just write 5. So in reality, the only place this is going to come up on a quiz or a test is going to be not if there's a number inside, like 5, but if it's a variable. And so, yeah. Okay. So if we're odd, then we end up exactly where we started. So here was my little mnemonic. It says if n is odd, then don't mod, it's a misspelling of modify, but don't modify. Or just leave it just like it is. If it's odd, don't modify. But if n is even, then the absolute value comes in. So here it says if n is even, then absolute value gets its revenge. I saw the word even inside of revenge. I told you it was lame. I'm sorry. Okay, so if it's odd, you don't modify it. Just leave it as it is. But if it's even, then absolute value gets its revenge. Nate? It takes a variable that we don't know the value of and gives us the final correct answer. Say it again. There's nothing times itself that will equal a negative. That's true. No. We're not making a fake number real. This guy right up here, negative 5 squared, became positive 25. So like by virtue of being an even power, we lost that negative. And so this is our way of saying, hey, even if you had a negative to start with, it's going to disappear. And absolute value is the magical thing that explains that a negative disappears. So we're not taking the square root of negative 25. That's a topic for another day later this semester. Right? It's not the square root of negative 25. It's that the negative disappears because it's raised to an even power. Okay, so we're going to update our rule. This was Jasper's rule from earlier. Last thing. So it says if n is odd, then what do we do with the powers up here? Jasper, what do we do with the powers? We divide them. Jasper said divide earlier. It's still true. And if n is odd, then you don't do anything. Like that's just the answer. Okay? But if n is even, we still divide. But what do we need to bring in? Absolute value. Okay? So it's just a small little detail. You get to divide, but if n is even, you got to put absolute value. Okay, activities start right there. I will walk around and check homework, raise a flag. I'll put the flags out too, and raise the flag if I can help.